Hello, and welcome to Lecture 3 of the Forces Unit in Phys 1104. In this video lecture, we're going to be looking at how to identify the forces that act on an object. Our main goal is to develop the skill of drawing good free body diagrams, which is a key skill for solving problems involving forces, and you'll use it not just in this course, but in many other courses that you take. I've already said a fair bit about identifying forces, but let me now lay out some general rules with a particular focus on contact forces. So whenever two objects are touching each other, or in other words, whenever there's a contact, the objects that are touching each other will always exert forces on each other. So the first step in identifying what forces act on an object is just to identify what it's touching. I'm going to start with springs because I've actually already done this in an earlier lecture, so I'll just re-summarize what I've already said. If a spring is pulled on so that it stretches, then it pulls back towards its relaxed length. And if it's pushed on so that it's compressed, it will push back towards its relaxed length. And those forces act along the line of the spring. Next, let me talk about strings, ropes, cables, and things like that, because they're a little bit like springs in the way they work. So let's think about a pack being lowered down a slope. And before I talk about the force on it by the rope, let me just take a brief diversion to the only field force that we'll care about in this course. So anytime we're on Earth, every object has a gravitational force on it acting downwards, and that's a field force because it doesn't require any contact. That's it. It always acts down. In fact, a good definition of down is the direction that gravity acts in. Okay, now back to contact forces. So with this pack, there will be a force which is a pull along the line that the rope lies along. And that's our general rule. Ropes and things like them always pull, and that force always lies along the line of the rope. Probably the most important set of forces for us to think about are the forces that surfaces exert on each other. So in the case of the pack, there would be a push out from the slope. The slope pushes perpendicular to the slope, basically to keep the pack from falling through the slope. And this is always true. Surfaces always push perpendicular to their surfaces. But then additionally, there can be a part of the contact force which is parallel to the surface, so that the total ends up being at some angle. So that can be in any direction parallel to the surface. In this particular case, I can tell you that it would be back up the slope, although it might not be obvious to you why that is. This force parallel to the surface is called friction, and it doesn't always exist. So surfaces always push perpendicular to the surface, and they may additionally have a component called friction, which is parallel to the surface. An exception to this rule that surfaces always push is that a sticky surface can pull perpendicular to the surface, but we're not really going to look at that very often. The remaining thing to be aware of is forces by fluids, and these exert a wide variety of forces, most of which we're not going to be concerned with very often, so I'll just briefly list them. Whenever an object is in contact with a fluid, there's a buoyant force on it, which is usually up. When things move through fluids, there's a drag force which opposes the motion through the fluid. Sometimes there's a lift force, depending on the shape of the object. And when an object is pushing gases or some other fluid out of itself, there will be a thrust force in the opposite direction. That probably feels like an awful lot of information in a hurry, but luckily it's not really that bad. So first of all, we won't really have to worry about the forces by fluids very much. The only one we'll look at very often is drag, and even that we won't look at much. And hopefully the rest feels fairly intuitive. Gravity acting down should be pretty intuitive, and springs, strings, ropes, and cables acting along their lengths should feel pretty intuitive. And surfaces pushing on each other should feel fairly intuitive. The one that's difficult that we're going to have to spend a lot of time on is friction. the force parallel to the surface that a surface exerts. Now we come to how you actually draw your free body diagrams. This is a key skill. You're going to use it all over the place in other courses, and it's tricky. It takes practice to do it well. So first, choose the object that you're interested in. It's the thing that you think is moving somehow, or which for some other reason you're interested in. And if you have a diagram, you might put a circle or a box around it. And now is a good time to start establishing letters that you're going to use to represent objects. Now list all the objects that the object of interest interacts with. Perhaps start with the objects that it touches, establishing notation as you go, and then things that exert field forces on it. Next, identify all the forces on the object of interest by each listed object. I can't stress the importance of the word on enough. Don't list forces exerted by the object of interest. They don't affect this object. They affect other objects, and they'll just lead you to confusion, so ignore them. Next, draw a center of mass symbol to represent the object. Remember, we're thinking of the object as a point. It doesn't matter where on the object the forces act. It won't affect the translational motion, and so we don't want to be distracted by where on the object the forces act. So we'll represent it as a center of mass symbol. Now draw the force vector for each force that you've already identified and label it. Pay close attention to direction. If you know some force is bigger than another, you might as well draw it that way, but now isn't really the time to be worrying about how big these forces are. Just get them pointed in the right direction. And finally, somewhere near the diagram, indicate the direction that you think the object is accelerating. Or if it's not accelerating, then say its acceleration is 0. Finally, it's a good idea to do a double check of agents and targets. If you're using the notation I'm using for forces, then the second subscript on every force should be its target, and they should all be the same. On your free body diagram, every force should have the object of interest as its target. If you find that by accident you've included a force where the object of interest is the agent, that doesn't belong here. That's a force exerted by the object, not on it, and it won't have any effect on the object's motion. So get rid of it. It doesn't belong here. Let's check your understanding of this process so far. So suppose a woman is standing in an elevator, and the elevator is going up, and it's speeding up as it does so. So I have reminded you that if the elevator is going up and speeding up, the acceleration vector of the elevator must point upward. So which of these is the most correct free body diagram for the woman? Not for the elevator, for the woman.